All right, welcome back. So now we're going to move on from the very basics of what we covered in the last lecture about individual perceptrons and how the fundamental concept of how we can use modeling neural activity to try and achieve computational goals. Those associated with being a thinking thing, right? So today we're going to talk about how we can combine those into multiple layered networks, multi-layered networks. So, like we said, we looked a little bit at neural structure. We examined artificial neurons in general, but also specific perceptrons, the kind of simplest version of those that have inputs, a threshold, and a yes or no binary 1 or 0 output. So we looked at how those individual and even small networks of those neurons can recreate Boolean functions. So the question is, at the end of the day, where we're walking towards is, what are we building with this? Are we trying to recreate an entire brain? Are we trying to recreate a mind? But on the way there, we need to recreate lots of different sub-functions, different ways to process information. But before we move on too quickly, I want to double back and make sure that this concept of the individual neurons is landing, the individual perceptrons is connecting. So remember why we're starting with these very simple Boolean functions. Like, if we're going to make neurons come together and process lots of very complex and interesting information, we have to start somewhere. We have to start with understanding how to algorithmatize the most simple informational operations using the simplest form of information, the bit, the on and the off, right? Remember Boolean operations. They transform bits. If I not a 1, it becomes a 0. If I not a 0, it becomes a 1. Right? This is the most simple way to move information, and it's cool. We're working toward it. And also, not is a unary operator. It just takes one value and inverts it, right? But you can also have the binary operators. Sorry, that's a little bit confusing. What I mean to say is operators that work on 2 arguments, kind of like plus and minus, right? Plus, you add two number values together and you get a larger number, right? And is a similar. These are similar concepts. So 1 and 0, so true and not true, true and false, would become 0 because not both of those inputs were true. But for or, either of the inputs can be true. 1 and 0, 1 or 0, 1 is the output because either one of them was satisfied. So remember, this is the most basic task for information processing. All of this Boolean logic, Boolean algebra, Boolean operations stuff is the most simple way to, because bits are the most simple unit of information, they're where we need to start to be able to achieve other kinds of processing. Every modern computer is using these Boolean operations to achieve everything. They do it billions of times a second, but that's how they're handling it. Your computer right now is doing that. My voice over this video is coming to you in form of 1s and 0s. So now let's think back to figure out what we're trying to do with these, to better characterize what we're doing here with these perceptrons to try and model Boolean functions. Think back to the Turing machine, right? It could do any mathematical function using an algorithmic series of steps. And remember, those steps didn't bear any real resemblance to the overall operation. You don't need the steps don't really make sense step for step, but we still achieved, remember, we actually implemented not, right? We took a bunch of 1s and 0s and we inverted them. It was a kind of a costly process, but we did it. So here we're doing something similar, but we're using a different rule set. Instead of having a whole bunch of rules and information coded up in a machine table, what we're doing is we're saying, okay, the rules of neurons, as close as we can figure and as well as we can capture those rules in math, there's only a handful. There's connection weights for input signals to be multiplied by, so I can either amplify a signal to excite the node, or diminish that signal, or even invert it to make the signal negative to inhibit the next node. Then the node itself has some kind of threshold, some level of value of activation it needs before it would produce its own signal. Either yes, I'm producing a signal, or no, I'm not. So those are the basic rules we're working with in this computational neural modeling stuff. And the question is, if we have to live by those rules, can we get to things like Boolean functions? How do we get to those things? I showed you last time some of this, but we're going to walk back through it a little bit, just to cover. It won't stick the first time. It's a little bit, it's hairy if you haven't seen this stuff before. So we're going to try and go through it at another pass with a little bit different flavor. So remember our Boolean functions. We won't dwell on this, but stop and familiarize yourself with it again. Remember, the idea is combining Boolean values and reproducing these sort of logical functions. So, for instance, remember the example last time I used pizza, right? I only like pizza if ham and pineapple are on it, right? So that's fine. I actually like that. It's fine. But if you just give me pineapple, I'm not into it. If you just give me ham, I'm not into it. So both ham and pineapple need to be present on the pizza for it to make sense, right? Oh, and I'm sure a lot of you are throwing your hands up right now about pizza toppings. Sorry, I couldn't have picked a more controversial topic, but here we are. So right? And it's a good way of showing like this is one of those cases where I need both to be true. Or is a different case of, well, I'll take either of them. So maybe a pepperoni or sausage is fine. Who cares, right? And also, sorry to my vegetarian friends here. I'm just using classic pizza toppings. But you get the idea, right? These different functions combine binary inputs and produce outputs that have meaning. They are a computation. They transform inputs into useful outputs. So, yeah, let's continue on to recapping the rules of perceptrons. So, remember, these are artificial neurons. They are attempting to emulate the plausible behavior of the way real neurons work. They are an abstraction. They are simplified math. There's a whole biological process happening inside real neurons, but this simplified math version of them is useful for modeling, right? Useful for our computational modeling goals. So a perceptron can take multiple input signals, typically one or two, but I think it's able to handle as many as you throw at it. And it will output just on or off. Either it will fire or it will not fire, given two inputs. And the way we create a function out of this, remember, we have only a handful of rules we can tweak about any given perceptron to try and make it work for it to still be reasonably neurally inspired, right? So we have the weights of the connections coming into the perceptron, which can be positive or negative, so they can change the incoming signal by a certain amount. And then the threshold of activation needed for that signal to fire. Now, an important little note here that I hope will be more clearly illustrated soon. The perceptron itself can handle activation values that aren't just 1 or 0, but it receives ones and zeros, and it will output, and it will sum them up according to its rules. And so while the signal is coming into the perceptron, it can do whatever math it needs to. That typically just multiplication and addition of these numbers, and then the threshold is what kind of brings it back into being a yes or no question. So whatever my activation level is, if it's below my threshold, I won't fire. If it's above it, I will. Back to ones and zeros, right? So it takes ones and zeros, it multiplies them and adds them. It doesn't really divide them. It multiplies and adds them, and then it will produce a one or zero of its own, right? So let's look at this a little bit more visually this time. So here's a little key. I've simplified the way we're talking about perceptrons. So the first one is a positive connection weight. So the incoming signal will stay the same, more or less. The weight is just 1. So multiply whatever's coming in by 1. Fine, good. Then we have the negative connection weight, which is the incoming signal will get inverted. So remember, it comes in as a 1 or a 0, right? An off or an on. But then it becomes math, and we can say, so if a 0 comes in, nothing happens to it. But if a 1 comes in, it gets turned into a -1 for when it's added up. Then we have the perceptron body. This is how we'll represent it today, using a square. And this is where we will think about the summed activation from the signals that are coming in. It can be positive or negative, and here I've got the range set, -2 to +2, just so we can sort of visualize it in a consistent way. And finally, yes, we'll move on. Finally, we have the activation threshold. I'll just have a big black bar on the perceptron body to show where and how much information it would need to be able to cross the threshold to create a firing pattern. So if the activation of the perceptron, the sum of all of its inputs multiplied by their weights is above this threshold, then the perceptron will fire off a 1. Otherwise, it does nothing, and it fires off a 0. It returns a 0. So let's remember NOT. Okay? NOT has one input, and it's a negative input, and we have set the threshold value at just below 0. This is the goal being to recreate that NOT function. So if I throw a 0 in here, the question is, does this fire? Let's follow it to find out. So the 0 comes in, it gets multiplied by -1, so nothing happens to it, that's fine. And then that means it's sitting at 0. But the threshold is just below 0, you can see. Meaning, yes, it does fire. This perceptron takes a 0 and says, I'll give a 1. Then it produces the 1, right? Now let's think about a 1. A 1 comes in, it gets multiplied by -1, so it becomes a -1. And that means it's halfway down into the negative section. It's way below the threshold value. Does it fire? No, it's not above threshold. What we've done is we've used the rules of perceptrons to create, the NOT function. The input of 0 becomes a 1. The input of 1 becomes a 0. Let's recap a couple of the other friendly ones we've seen. And so what signals would this one need in order to fire? Look, it's got 2 inputs coming in. Remember, they're going to get summed up, and they're both positive, right, in this case. And the threshold is set pretty high. It's set just below 2. What that means is you have to have a pretty high amount of activation for this one to fire, otherwise it won't. So what do you need? You need them both to be 1s, right? To cross that threshold, both inputs have to end up as 1. Or they have to start as 1 so that they can end up above the threshold and create a 1. Otherwise, it's 0s. Remember, and needs both, right? Both is the key. How about OR? All you do to create an OR function is you lower that threshold a bit so that getting either a 1 in either slot will be enough to push it above threshold, but getting 2 zeros is still below. I hope this is making sense, right? So either signal can be 1. We're going to make it past that finish line either way. So either and for or and both for and. Okay. So this is cool. I hope this is illustrating a little bit better the way that a perceptron handles this information to convert two binary inputs into a binary output. Now, remember what we talked about before. These are nice. These are all pretty easy because they are linearly separable. That means that I can literally draw a line to separate the outcomes in their respective problem spaces. So the not function, everything above the line is a 1, everything below it is a 0, and everything above is a 0, everything below is a 1. Same with or, but it's set in a different spot. To visualize that a little more clearly here, remember the and function, we can see the little graph here, right? If I take in, so the graph is showing the inputs, right? So the x-axis is one of the inputs and the y-axis is the other input. I can draw a line right there and kind of group the inputs based on that. And is only going to be dark, or otherwise considered to be a firing signal, in that upper right region of its particular graph, right? It takes a lot of signal from either source to get there. Whereas an OR function, you can set that threshold lower, right? You'll fire off in a lot more different cases that are, as long as it's not 0. The trouble comes, even with these fairly simple Boolean logic operations, the trouble comes when we get to something a little more complex like XOR. If you remember XOR, this is the exclusive OR, right? This is the situation where you only want one or the other, you don't want both, right? You don't want, and you don't want neither either. So this will be the case where, say you only need one person to help, and you don't need multiple people to help you on a job, for example, but you still need somebody. So, either your friend Dave or your friend Jen is going to help you. You don't need both. You're not going to waste both their afternoons. Although it is nice to have more people. But the point is, that's the idea. You don't want both. You don't want neither. You only want one. You can't draw a line through that. That's tricky. So this gets us into a scenario where the simple perceptron, the humble perceptron, can't do this on its own. We are subtly edging towards the topic of today's lecture. I know we've been at it for a little while, but I want to continue this thread, right? So remember XOR. Remember this is exclusive OR, XOR. It wants that 1 or 0, or sorry, it wants either signal, it'll fire, but neither or both doesn't want it. So it's not linearly separable. A single neuron, a single perceptron can't handle this. But a small network can. So let's try to build it. With what we know, right? How do we handle this? So let's look at what can we actually do in terms of transforming information using individual perceptrons. So OR gets us pretty close, actually. Compare OR. Look at just the outputs of OR. OR actually gets us pretty close, right? XOR seems to be this kind of splice of these two. So OR, 3 of its outputs are correct. For 0 and 0, it gives a 0. For either of the other inputs being true and the other one being false, we get a 1, right? So OR and XOR are close. They're close together. That's kind of cool. Even better is that AND is only a 1 when in the only case where OR is incorrect. So what we're seeing here is we can combine these two. We can combine OR and AND, at least the values that come from them, pretty straightforwardly. We can say, hey, as long as the first three values just pass them straight through, but the last value we need to stop it. We need to operate on it. So we can do that because we have a tool in our kit. We can invert the AND signal. So if we're combining a bunch of zeros, that's easy. Those get added together. They do nothing. They don't do anything to the OR signal. But if the AND, when the AND signal is active, we can use it, multiply it by -1, and add it to the OR signal to negate it entirely, getting us that ultimate XOR that we wanted. So what this means is we're going to need at least 2 perceptrons in this network, and then an additional third perceptron to do this kind of differentiation, this comparison operation. So let's build it. Let's actually do it. So remember, we're going to take 2 signals, signal 1 and signal 2. They're both binary, 1 or 0, and we're going to first we want to compute the AND of them, right? So we need an AND perceptron waiting. We're going to wire both signals up to that AND. And we need an OR perceptron. We can wire both signals up to that OR perceptron as well. And then finally, remember what our goal is. We're going to invert the AND, but otherwise just pass the OR straight through. So we're going to have a third perceptron. We're going to pass the OR information there, and we're going to invert the AND information, and we're going to add all those together. Set the threshold in a similar spot to the OR, because we don't need, it satisfies most of the conditions. We can try that to start. Spoiler is that it works, but this is the kind of thing you need to maybe train the network for. So we should give this a name. We're going to just call it the comparer. And then finally, ultimately, we want to know what is the output of this little bitty XOR perceptron network. So let's look at this. Let's watch it. So we're gonna do a table, all the different values. So signal 1, signal 2, what the value of AND is in that case, what the value of OR is, the comparer, and then finally whatever the output is. So let's start with the first case. Let's do 0 and 0. 2 zeros coming in, right? And we can sort of follow this. Okay, 0 and 0, that's going to AND out to 0. They're not going to cross threshold. 0 and 0 isn't going to cross threshold for an OR either. That's pretty straightforward. And then our comparer, well, the AND is going to get negated, but it's still a 0, so it doesn't matter. The OR is going to get negated, but it's a 0. Nothing matters. So 0 is less than the comparer threshold too. So ta-da, we just straight dump that 0 straight through. Okay, now let's get a little more involved with it. 0 comes in, and a 1 comes in. So first signal is a 0, second signal is a 1. This is actually going to be an identical case for the other one, so we'll skip past that. But so in the case that only one of these signals is a 1, what happens? Well, the AND still gets 0, right? Because that's not enough to cross its threshold, right? The OR, looking at the OR, that is enough to cross the OR threshold. Great. So the comparer, well, the AND is still not active, so it's not really influencing the output. It doesn't do anything at this stage. The comparer, on the other hand, well, not on the other hand, just straightforward. It just says, the OR signal, I'll take it. And it does the same exact thing. It outputs the same signal. So, great. So far, we're seeing that the AND, as long as it's got a 0 in it, it doesn't influence the outcome at all. So we can speed through this next one. The OR, the AND doesn't compute from the 1 and the 0. The OR does, and that gets passed through the comparer, and great. Finally, we get to the most interesting chunk. So the question is, what happens when I have both of these active? So a 1 and a 1 come in. Well, this time the AND is a 1, because that's enough to cross its threshold. And the OR, of course, that's plenty to cross its threshold. So we now have a 1 and a 1. The comparer now is going to do its job, and that is, I'm getting a 1, a positive 1 from the OR, but I'm getting a negative 1 from the AND. I'm going to sum those up to be 0. That doesn't cross my threshold. Ta-da. I've used the and to invert that final bit of the or that wasn't correct. We did it. We used a 3-perceptron network to create the XOR function. We have done it. We have created, because XOR was just out of reach by a single perceptron, we've now created a small network that is able to actually perform this slightly more complex Boolean function. And that illustrates, I hope, the direction we're going to start going now. Because we've gone from the most basic individual neurons, what are those capable of, to, oh, wait, I can do something more interesting. So, altogether, perceptrons are these simulated neurons. They are fairly biologically plausible, right? They follow the same sets of rules that actual neurons do. And they can be configured to fit any Boolean function. You just have to keep combining them. If you can't reach it with a single perceptron, you can reach it with a set of them that can all invert one another. And because Boolean functions are the basis of so much information processing, that means we can do a lot of information processing using a neural approach. So, this is cool. This is showing that you can scale this up pretty hard. You could actually build an entire modern computer out of perceptrons. You would not want to; they're super inefficient, but you can. It's possible. Well, the original perceptron. More modern neural networking solutions use a bunch of hard-coded, powerful processing going on at the chip level. So. But that's just nerd speak. So, okay. Now, we talked last time a little bit about some of the cooler things we can do. That these, if you do scale up to a large network of these perceptrons and simulated neurons, we can get a few other cool features like graceful degradation, partial pattern matching, learning. Right? And so a big question is, how do those things work? So let's talk about learning and training in neural networks. There are two big categories for how to train a network. And before we move too quickly, the idea here being that you can, because it's just weights and thresholds, which are just numerical things, right? A weight doesn't have to be 1, it could be 0.1, it could be 0.10. I could combine 30 different signals with very low weights, and when one big signal with a very a high negative weight, and something, complex processing happens, right? So one of the coolest features of these things is that it's really easy to adjust those knobs, right? Oh, if this network isn't working like this, I can tweak it a little bit, and now maybe it'll work. I can tweak it a little bit, maybe it'll work. That's called training. That's called learning. That's called everything. Everything that you do, you change your patterns just a little bit in order to capture a different pattern of activation, a different behavior, right? So, in neural network learning, there are two big categories. There's supervised learning, which is when you are giving feedback to the network so that it can have a sense of its own error. So if you say, oh man, you guessed that 10 times 10 was 4, you are way off. It will tweak its settings. It will adjust its thresholds and its weights in response to that. And especially because you're able to say, hey, you were way off. That's a different thing than, hey, you were just slightly off, And then there's unsupervised learning. So this is less about knowing the outcomes that you're supposed to be getting, and more about just when the neurons fire together, they will become more positively associated and negatively associated. So the idea being that there can be a process of these neurons sort of, oh, we're both firing, we'll probably fire together in the future, that kind of thing. So let's talk about unsupervised learning first. This is the second category here, the no feedback, right? How do neurons learn without feedback? So this is called Hebbian learning. God, if only I could pronounce things. Neurons that fire together wire together. That's something you should drill into your brain. It's a useful reference point for talking about a lot of neural stuff. It's not always exactly, perfectly true. Everything you're learning, you'll learn more advanced versions of as you climb up the tree. But it's a good rule of thumb. Neurons that fire together wire together. And this is based on some neurobiological findings. If neurons that are physically near each other, or rather, not physically, but like they are networked into the same firing patterns, and if they fire at the same time, it's just more efficient to make it so that they all fire together, right? So that when one triggers, the other one will trigger, as opposed to having to detect and calculate. So it doesn't need any feedback from the world. It doesn't have to know anything about what it's looking at and dealing with to be able to build a network that's able to make sense of it. So let's look at an application of this. Pattern recognizers. Okay, so think of an image as a pattern of colored inputs. It's just a bunch of pixels, just to spoil that for you. The images you're looking at are just an array of colored dots, right? You can imagine giving those to a network as an input signal. 3 different values for each color, those 3 values for each dot, and that's a bunch of math, but that's great. I can give that to a network. So using this Hebbian learning, I can show a network a bunch of images and just let those little the activations of the incoming images sort of let the neurons wire together, and then ultimately you can use it to detect those patterns. But let's spend a moment here. So check this out. If I showed you these 2 birds by default, you probably wouldn't distinguish them very much, right? But let's look at the facial areas, the red squares. So in the top image, we have the Bohemian waxwing. And if I show a network hundreds of or even thousands of photos of this creature, of this bird, the neurons that are responding to red, for instance, will start to fire every time you see this type of image. And they will get used to firing together, and they will get used to activating in conjunction with these very dark black responsive neurons, right? So as you expose the network to this image, the image activates all the different little neurons of the network. It doesn't have to know where it's going. It's still going to, they're going to affect one another. Oh, all the inputs came in. A neuron further down will fire based on the inputs, etc. And the way that the Hebbian learning helps this is it says, oh, these things are always next to each other. I'm forming an association between them. So you see the little kind of the blush on this particular bird, the Bohemian waxwing, is red next to this very dark black. But also other things, like this dark black occurs next to negative space, the sort of lighter colors of the sky, of the background. That's a sharp edge. I should be looking for that edge. I can sort of detect this curve. What that ends up producing is a network that is very well wired to activate become most active. All of its neurons will become most lit up. It will fit the visual image of this bird. And the cool thing about the neural system involved here is that you can show it slightly different versions of it. It doesn't have to be the exact same image every time. It starts to pick up on these abstracted patterns. How exactly it does that, we will delay for a longer discussion later. But this is how it works. Now, I've been ignoring the cedar waxwing. So why is it here? What is it illustrating? Well, if I show the cedar waxwing to the Bohemian waxwing network, just remember looking at their faces, the Bohemian waxwing network is probably going to light up okay. It's got the same rough shape. It's still kind of birdish. It's got the same kind of eye and similar beak, but it's missing some big components. So it's not. It doesn't have that sort of the black, the chin, whatever you call that particular region on the bird. It doesn't have the blush on its face. So certain sets of the neurons that have been trained to wire and fire together will be dark if I show the Bohemian waxwing network a picture of a cedar. Meaning that network is trained to recognize Bohemian waxwings, and it's not trained to recognize cedar waxwings. But that's fine. I can build a whole other network to recognize cedar waxwings. And then I could situate those in a complex network space, blah, 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 whatever. But the idea being, this is how just exposing a network of these all interconnected neurons, the process of Hebbian learning helps them to update their settings to be able to be most activated for under certain conditions that it has observed before. This is how we create these pattern recognizers, and they are big, they are huge, they are great. They are all over the internet now. They're all over your computers. They're all over your life. So, yeah. Okay, so that's an example of unsupervised learning, where you don't have any specific outcome desired. I mean, we sort of do. We want to train it to see the Bohemian waxwing, but we're not giving it feedback. We're just saying, hey, observe the world, and whatever neural connections come, that's cool. On the other token, we have supervised learning, and this is a little more. It's more effortful, but it's a little bit more powerful in terms of helping these systems train. So the supervised learning rule for perceptrons specifically is the delta rule. And it's just a formula for adjusting the perceptron's threshold and weights based on how wrong it is, right? So we can look at the delta rule. We won't need to hang out with it too long. The change in my threshold is equal to the learning rate times the error, and then the change in each of the weights is it compares that. Look, we don't need to handle all the math. The point is, it understands what the inputs were and what the outputs were, and it also understands how wrong it was, its error rate, how far off its guess was. So again, if I'm telling this network, hey, what's 10 plus 10? And it comes out with 13, we'll say, ooh, that was close. You were off by a lot. You were off by 7. So then it'll say, okay, based on 10 and 10, I might adjust my weights because some of those weights were probably too small. And I'll also update my threshold a little bit. And you can see how using that process, this perceptron will narrow in on, I mean, it's not designed for a single perceptron to do 10 plus 10, but just the concept is, say you even have several of these neurons, these perceptrons, each individual one of them can use this delta rule to say, ooh, something told me I was wrong. Let me update, let me tweak a little bit. Let me try let me take another swing at this. Now, again, we're getting into the problem of the delta rule. This is really great for individual single perceptrons. There's a theorem proving that a single perceptron will always converge on the solution if you use this delta rule to update it. It might overshoot, but it'll eventually wiggle back and forth until it's at the right solution. And there's some evidence that these rules are plausible with the way that neurons actually update. There's a whole complex process involving proteins and changing, the neuromodulators and something, etc. Come to the Brains, Minds, Consciousness course for a little more on that. Little plug, sorry. But the idea is that This makes some sense, but remember that the rule only holds. It's only guaranteed that this will work for individual perceptrons. And why is that a problem? Well, imagine, I mean, no perceptron, no neuron in the brain lives alone, right? They are all upstream and downstream from one another. They're all triggering one another, etc. So, if the error is only able to be known after, oh, I wrote this down, but then my teacher gave me a red mark, that means error. How the heck is the neuron a couple of steps back supposed to actually get this feedback, right? The error, there's not multiple directional connections. That you can't send information backwards, or can you? So the solution that neural modelers came up with is backpropagation, which is a system of applying the delta rule, the updating function, right? Oh, I got an error, I will update my rules. But applying it backwards across multiple neurons. So you can go back and back and back. You can have many perceptrons that will send their error information back and say, hey, I was wrong. Hey, you were wrong. And then, hey, tell the other guy he was wrong, right? Which is useful. It's a useful solution, right? This allows for the information to move forward, and then we also transmit the error backwards, and everybody updates all their stuff. So it helps to update every individual perceptron's function. So here's how backprop works. The middle layers and even the first layer don't get any feedback at all, right? Under the normal circumstances. Feedback only happens at the output end, only after we've already computed the full XOR, right? So the idea here is that in backprop, the responsibility for the output error is propagated backwards. Haha, backprop. So it's based on each individual perceptron can compute its contribution, so how it has connected to the ultimate result, and then compute its own responsibility for the error. And then it uses that responsibility value to update itself in proportion to the error. So, again, there's lots of math going on here. We don't need to dive in deep on that. But the idea is now I can receive an error signal at the end of all my processing, and I can update every single perceptron in my network. And so here's the thing. Does it work? This is an interesting solution. It's a pretty straightforward one. Well, the math is not super straightforward, but it's also not out of, it's not off the wall crazy, right? The question is, does it work? The answer is, yeah, it does an okay job. It does a pretty good job. So backpropagation networks are shown to be able to compute any Turing computable function, which is really cool. That means math, that means logic, that means Boolean functions, obviously. That means like calculus, right? Like anything that a Turing machine can do, aka your computer, this can be done by a backprop network. That's pretty neat. That doesn't mean that a single network can handle every function of the computer. You'd have to build multiple networks with different varieties of functions. But it's shown that you can use backpropagation to train any individual Turing computable function, which is pretty cool. But the simple perceptron convergence rule is proven to always converge on the correct solution. That's not true of backpropagation. You can swing wide in backprop. So you can get stuck in situations where, as you're trying to train this network, it just can't escape a bad answer. And that's because it's too complex. The reason that back to linear separability, right? The reason an individual perceptron is able to always find the correct answer, provided there is one, is because an individual perceptron can just keep changing its weights and thus adjusting its line, right? Its line in the state space. and eventually it will find it. It has to. If it's wrong, it keeps sliding that line. It's like a linear fitting situation. The problem is, with the more you add complexity to it, you open up the door to things called local maxima and minima. So sometimes when you're searching, and this is true just like in life too, but also for math and also for perceptrons. So when you're searching, sometimes you stop looking because all the other possible nearby choices seem worse than your current position, right? This is called a local maximum or minimum, depending on which direction is positive or negative or whatever. The idea is you're stuck at this local little hump. So lots of machine learnings are vulnerable to this because what this means is that I might get stuck on a solution that doesn't actually work, right? That's not great. I get stuck on a solution because there's no way for me to adjust my weights subtly, no matter how wrong I am in this scenario of a local maximum. I can't reach the actual maximum, the actual desired state, because the update rules aren't enough to get me to a different scenario where I can notice a better option. That's pretty key, and that's not just backprop. That's any complex system and any complex search through a space to find the proper solution has these local minimums and maximums, and so does the world. You'll never know what you might have missed. Sorry, that's a bummer, but it's a thing to keep in mind. So, sorry, slurps. Let's look at some examples of. There's this little website you can go to. It's pretty neat. It's a demo to show how training a simple network works. This is actually the XOR network, and the idea is it starts off with no knowledge. Its weights are all wrong. Its thresholds are all wrong. I give it 2 inputs, and it will propagate through the network at just the default settings. And then at the output, it says, hey, was I right? So I give it 0, 0, and it dumps out a 1. And it says, hey, was I right? And my system says, obviously not. You're not right. That's silly. You can't give a 1 at 0. So it says, all right, I will backprop the error to my nodes, and they will all adjust themselves. So next time I give it 0, 0, it will move through the system differently. I'd say just go play with this toy. It's fun. I might put a link to that somewhere. You can get it in the slides, the downloadable slides. So let's look at several ways that this system actually panned out. It will update a little differently every time, so it's not deterministic. It's a little bit random the way that it trains itself, but it works. It illustrates the way that this happens. Let's look at my output functions, right? In this case, this first time around, I ended up with this state space of, so when I give a 0 and a 0, it just barely is within that space that, yes, that's incorrect. I will also output a 0. If I give a 1 and a 0 or a 0 and a 1, cool. I'm in the green. So to describe this space, the green areas are the mathematical regions where I'm outputting a 1. The red areas are the mathematical regions where I'm outputting a 0. And those regions are defined by the thresholds and the weights of the nodes, right? We don't have to know exactly how they're defined, just that's the case. So let's look at a second example. A different time I trained the system, and this took like, seconds, right? Not even seconds, quarter second to train each time. It's a different space, right? But we're seeing it still works. It still captures the function, right? It's accurately getting when I'm only going to give a 1, a green, if I'm in the one or the other case. And in the other 2 cases, I should give 0 responses. Great. Another case here, another whole different way that the system would set itself up, but it works. Again, it's working. So these are different weights found that create different response spaces, but they still converge on the correct solutions, right? The training target is, when I get 2 zeros, give me a 0. When I get 2 1s, give me a 0. Otherwise, give me a 1. The The trouble is, though, that there are times where, as I said, you can see how these are different every time. They all reach the correct conclusion, but they arrive there at slightly different ways because the way they're set up initially and the path they take is a little bit random. So, this is a scenario where we wound up with a local minimum where it could not get out of this situation. It found its stable solution was wrong because it was not able to update itself, again, just because of the random path it sort of took while it was trying to train itself. Another scenario here, a different kind of space. These are both cases where this backpropagation and training rule couldn't figure out XOR on its own. It wasn't able to just train itself straight into it. And XOR only needs 2 lines. XOR was fairly straightforward. So even just one uptick from a simple, singular solution in complexity made it so that there were times that it didn't actually solve the problem. So, yeah, in these cases it was stuck in the local minimum or maximum, whatever we want to call that in this case, and it couldn't successfully converge, even with just XOR. So, that shows there is a weakness to it, but it's still powerful, and it's still very, very cool stuff. We're able to train whole networks to solve different functions for us just by saying, hey, here's what the function ought to be, get used to computing it for us, using your little algorithmic rules. So, now, there is another issue with backpropagation, and that is there's not actually good evidence. I think there is some, but not good evidence, and there's some evidence to the contrary, too. Many of these things are continuously debated in this very active field. So there's not much biological plausibility to the way this works. So the brain is this huge distributed network of neurons. They're all active, like pretty much, they're all firing all day. That 10% thing you've heard, that's gibberish. That's garbage. It's not true. You're using all your neurons, otherwise they would die. So, in that case, in that huge, massive, big ball of all talking and interconnected neurons, where's the middle layer? How far back should any error go? Does my whole brain lock up and get punished when I realize I marked the wrong answer on my, on my W2s? Like what part, what is the rule for how this works? And also, how exactly does the information propagate backwards? A lot of, the way that neurons communicate with each other is one directional. One neuron will spit out neurotransmitters at another neuron and affect it. So the question is this an issue just for backprop, or is it sort of something more important about how learning happens biologically? So, yeah, let's see. What have we covered today? We doubled back and talked a little bit more about perceptron Boolean functions and how a single perceptron can handle them. I hope it was a second exposure, a little bit different visualization. I hope it helped to solidify that idea. We also looked at some of the rules for learning. So simple perceptrons use the delta rule we looked at 2 kinds. So we looked at a little bit of unsupervised and a little bit of supervised learning. We also looked at in terms of the supervised learning, we looked at the delta rule for simple perceptrons, and then backpropagation, which is a modification of the delta rule for perceptron networks. And we saw some issues with backprop. The way the local minima and maxima can cause it to not be able to find the right solution, and it's also not clear that the brain is capable of implementing this exactly, this kind of propagation. So, all right, that's it for today. Thanks for watching, and I hope y'all are staying safe and healthy. It's quite beautiful out today, so hope you're getting a little bit of air. Yeah, so next time we'll talk a little bit more about these neural network approaches and some cool, weird examples, and then we'll see what's on next. Take care.